minus m1g is equal to m1a. Solving these two equations, we get a is equal to m2 minus m1 by m2 plus m1 into g. Now, this is the magnitude of acceleration of this downwards and this upwards. Now, vectorially when we write, we have to choose coordinate axis. If you choose coordinate axis upwards as y-axis, towards right as x-axis, then a1 is equal to a j. It is upward positive direction, whereas a2 is minus aj, and acceleration due to gravity is downwards. Acceleration due to gravity is g minus j. Substituting there, we get a1 is equal to m2 minus m1 by m2 plus m1 into gj, that is the acceleration upwards a1. Acceleration a2 for this block is m2 minus m1 by m2 plus m1 into g minus j. Both are of same magnitude, but directions are different. Upward direction we are taking as positive y-axis, downward direction as negative y-axis. Therefore, the accelerations are like this. Therefore, acceleration of center of mass comes out to be m1a1 and m2a2 divided by, therefore, this is going to be m2 minus m1 by m2 plus m1 whole square into g minus j you will be getting. So, the acceleration of center of mass is m2 minus m1 by m2 plus m1 whole square into g minus j, means acceleration is downwards towards negative y-axis. So, acceleration of the center of mass in the case of Atwood's machine, where the blocks are moving in different directions, acceleration is downwards. This value is same whether m1 is greater than m2 or m2 greater than m1. Even if m1 is greater than m2, this is negative, but square of that is positive. Means whether the m1 block of mass m1 is greater than m2 or block of mass m2 greater than m1, the acceleration of center of mass is downwards only. Therefore, this is how we calculate the acceleration of center of mass. Next one is the equation. We now concentrate on this equation. For a system of particles of constant mass, F external is equal to m into ACM, which is also equal to dp by dt, that is rate of change of total momentum. This is P total, which is also equal to dp center of mass by dt. This is Newton's second law. Just now we have derived Newton's second law of system of particles. Now, in case if F external is 0, means net external force acting on the system is 0. If the system is not acted upon by external force, irrespective of what kind of internal force are there, whatever may be the internal forces, in case if the system is not acted upon by any external forces, in such cases what happens? ACM becomes 0, acceleration of center of mass is 0. Center of mass will not be accelerated in the absence of net external force, in spite of internal forces which are acting. ACM is 0, or P total is dp by dt is 0, or dp cm by dt is 0. When net external force is 0, acceleration of center of mass is 0, rate of change of total linear momentum of the system of particles is 0, or rate of change of linear momentum of center of mass is 0. From this, what we can conclude is P total which is also equal to PCM, total linear moment of center of mass, is constant, and from here VCM is 0 or VCM is constant. Okay. In this case, what we write, in the absence of net external force acting on the system, total linear momentum of the system of particles, which is also equal to linear momentum of center of mass, remains constant, or the velocity of center of mass or velocity of center of mass is either 0 or velocity of center of mass is a constant. Now, this equation is law of or principle of conservation of linear momentum. This is called law of conservation of linear momentum. Under what conditions conservation of linear momentum principle is valid or law is valid? In the absence of net external forces, the total linear momentum of system of particles remains unchanged or remains constant or remains conserved. That is what we call it as law of conservation of linear momentum. That is, P total is constant for when if net external force is 0. Net external force acting on a system of particles is 0. The total linear momentum of the system of particles is constant, and total linear momentum is due to sum of the linear momentum of the particles. That implies P total is equal to P1 plus P2 plus P3 and so on Pn, where P1, P2, P3 or Pn are linear moment of individual particles. The total linear momentum is obtained by vector sum of the linear moment of individual particles. So, vector sum of the linear moment of individual particles is the total linear momentum. In the absence of net external force, this quantity is constant. So, that is what we call it as conservation of linear momentum, the sum of the vector sum of individual linear momenta. Now, during the course of motion, in the absence of net external forces, in case if internal force are there, individual momenta may change. P1, P2, P3 may undergo changes because they are acted upon by forces which are due to internal. But in the absence of net external forces, though individually they are changing, but their sum, vector sum remains constant. That is what we call it as law of conservation of linear momentum. But in a vector form, P total we can write in the as a component form Pxi, Pyj, Pzk, where I, Pz, Px, Py, all these are the components of the total linear momentum vector along coordinate axis. When total is a constant, then we get this is a vector equation, and we get 3 scalar equations which are simultaneously satisfied. Px is constant, Py is constant, and Pz is constant. So, therefore, conservation of linear momentum of a system of particles valid in the absence of net external forces provides us 3 equations which are x direction linear momentum constant, y direction linear momentum is constant, z direction linear momentum of the system is constant. These are the 3 equations, scalar equations we get from the conservation of linear momentum.
డియర్ స్టూడెంట్స్, ఈనాటి ఎపిసోడ్లో హాలో కోన్ మరియు యాక్సిలరేషన్ ఆఫ్ సెంటర్ ఆఫ్ మాస్ గురించి తెలుసుకున్నాం కదా. రేపటి ఎపిసోడ్లో సెంటర్ ఆఫ్ మాస్లోని డిస్కషన్ ఆఫ్ అప్లికేషన్స్ అండ్ ప్రాబ్లమ్స్ గురించి తెలుసుకుందాం. కీప్ వాచింగ్ KAB టెలివిజన్. ఇక ఈ కార్యక్రమంపై మీ సలహాలను, సందేహాలను మాకు పంపాలంటే eClasses@KABTV.net కు ఈమెయిల్ చేయండి.